All right, today we're zooming way in. We're going past what any microscope can see to look at the fundamental building blocks of reality itself. We're talking about the tiny particles that make up you, this screen, the air you're breathing, everything. We're talking about atoms.
It's a question that sounds so simple, right? But the answer is honestly pretty mind-bending. If you could just keep zooming in, past your skin, past your cells, what would you actually see at the very bottom of it all? Well, let's find out.
So to get our heads around this, let's use a simple analogy. Think about building a house. It's not just a big blob of house stuff. You need very specific parts that do specific jobs. You need a solid foundation, you need frames for the structure, and you need fasteners to hold it all together. The universe, it turns out, is built on a very similar principle, just on an unbelievably small scale.
Every single atom, no matter what it is basically its own little construction site. And on that site, you've got a crew of just 3 main players. So let's meet them.
First up, we've got the proton. You can think of this guy as the foreman on the job site. It's got a positive charge, and it hangs out right in the center, in the nucleus, calling all the shots. And here's the most important part. The number of protons is what decides what the atom is. It's like the atom's permanent, unchangeable ID badge. Working right alongside the foreman is the neutron. This is the reliable assistant. Neutrons, as the name kind of suggests, have no charge. They're neutral. Their main job is just to add some heft, some mass, and to keep that central nucleus stable. They're like the sandbags holding the whole operation down.
And then, there's the electron. These are the workers, just buzzing with negative energy, and they are constantly zipping around the construction site. They are incredibly tiny and unbelievably fast. They don't stay in the center with the bosses. Instead, they orbit it, creating this huge zone of activity.
Now, let's focus on that nucleus for a second. This is the control room, the very heart of the atom, where our foreman protons and assistant neutrons are packed together. And this is where things start to get really weird. To try and picture the nucleus, imagine this. You take a full-sized car engine, all that heavy metal, all that weight and power, and you somehow squish it down until it's the size of a single grain of sand. That's the kind of mind-boggling density we are talking about here. It takes up almost no space, but it has almost all the mass.
Just think about this number, 99.9%. That's the percentage of an atom's entire mass that is crammed into that impossibly tiny nucleus. Everything else, all that space where the electrons are buzzing around, accounts for just a tiny, tiny fraction of the weight.
Here's another way to think about it. If you could blow an atom up to the size of a football stadium, the nucleus, the part with almost all the mass, would be nothing more than a tiny marble sitting on the 50-yard line. But, and this is the absolutely wild part, that single tiny marble would weigh as much as every single person sitting in the stands.
So wait a minute. If the nucleus is just a marble in a stadium, and the electrons are like tiny dust specks flying around the stands, what's in between? What's filling all that space? The answer is nothing. The atom's biggest secret is that it's almost entirely empty space.
This, of course, leads to a very logical and very fair question. If you're made of atoms, and the floor is made of atoms, and all of those atoms are almost entirely empty space, why aren't you a ghost? Why doesn't your hand just pass right through the table when you touch it?
The answer is all about forces. Think about a chain-link fence. It's mostly empty space, right? Mostly holes. You can see right through it, but you can't walk through it because the thin metal wires create a solid barrier. It's the exact same idea with atoms, but instead of metal wires, the barrier is made of a powerful, invisible force.
That barrier is the electrical force. Remember how protons are positive and electrons are negative? Well, opposites attract. And that attraction acts like an invisible leash, keeping the negative electron dog in orbit around its positive proton owner. It's also what makes the electrons in your shoe push back against the electrons in the floor, repelling each other so they can't pass through.
Okay, so we've got our crew. Protons, neutrons, and electrons. We've got a super dense nucleus and a whole lot of empty space. But why does any of this matter? Well, because this simple 3-part structure is literally the blueprint for everything in the universe.
The identity of any element comes down to just one thing, the number of protons. That's it. One proton gets you hydrogen, a basic but essential element, kind of like a screwdriver. 6 protons gives you carbon, the super versatile building block of all life, like a Swiss Army knife. 26 protons, now you've got strong, heavy iron, a sledgehammer.
And once you understand this basic blueprint, you suddenly start to understand, well, everything else. Why do metals conduct electricity? It's all about how their electrons behave. Why is a diamond the hardest thing we know, while butter is soft? It's just how their atoms are bonded together. Rusting, burning, dissolving, it all comes back to how these tiny building blocks are interacting with each other.
So you see, this isn't just about memorizing some facts for a science class. When you start to understand the atom, you are learning the fundamental instruction manual for the entire physical universe. You're learning the blueprint of reality itself.
Which brings us all the way back to the beginning. You, me, and everything you perceive as solid is actually made of these tiny particles, which are themselves almost entirely empty space, all held together by invisible forces. It really makes you wonder, doesn't it? What are we, really?